if there's going to be errors, which do you prefer? It's almost like a precision recall. Would you prefer a model that refuses to answer more, sometimes be quite frustrating because of that? Or would you prefer a model that runs the risk of, as it were, hallucinating a response? And so these are really, really tricky things to like drill down and get right.
Today we're going to give you an insider perspective on Retrieval Augmented Generation, or RAG, as you've probably heard it mentioned. We speak to Patrick Lewis, who is the guy who helped coin the term. He's a leading expert in the field. He works for Cohere, and he's also a very cool guy. We will deep dive into the evolution of language models, going all the way back to the days of Mikolov and Word2Vec, to modern language models and beyond.
Even back in 2015, this algorithm, when you did this clustering of the elements, they clustered in such a way that they reproduced the periodic table. It just had like read the literature and had discovered the periodic table within it.
We share practical tips for implementing RAG systems in large enterprise, and this is the reason to use Cohere, by the way, because they're extremely good at that.
Prompt engineering to get augmented generation working is really, really hard. And sort of what we do at Cohere is try and build like actual like prompt templates that the model has like very, very concrete like awareness of in the way that we post-train.
It would also be remiss of me not to mention that the Brave Search API is partnered with Cohere. So if you want to do some really cool retrieval augmented generation now on the best search index on the web, sign up to the Brave Search API at brave.com/API. Enjoy the show.
Let's talk about, like evaluation. So like there's evaluation for RAG, which is quite specific, and you tend to like try and measure a few different things. There's that answerability thing.
Yep.
Is this answerable? Is this not? There's these sensors of faithfulness, which we usually use these grounding spans or these citations as a way of making that concrete. Like, is everything grounded? Are we missing anything? Is there other things that shouldn't be grounded, but the model has produced a mistake there? Like that's how we get a grip on that problem internally. Then there's, like fluency. Is this model good or bad in terms of like the structure of its answer? Does it like feel like a high quality response? And then perceived utility. A lot of these terms come from a really great paper that Nelson Liu did from Stanford a year and a half ago, I guess now. It's like a really nice piece of minimal things that you need to like study. Verifiability in generative search engines, I think it is. Yeah. It's a good paper. Perceived utility is like a term that goes further back than that, but it's like, does it feel like the information need was addressed, even if it was wrong? So like, did we do the right thing, ignoring the documents existing for a moment? And so you need to have both good fluency, addressing the information need, and the actual like citations tell you if you got it right or wrong, like in terms of the faithfulness. All of those things are really hard to measure, and there aren't good data sets out there to just like benchmark against that do this anymore. The quality of our models has massively outpaced data sets that we use to evaluate RAG. And also our like consensus on how we should evaluate them. So our metrics are lagging pretty hard. We're still in a mode where a lot of time we're just using simple one-hop general knowledge questions augmented with Wikipedia, which is what we were using back in 2020, like same data sets, but now our scores are just outrageously high. And our metrics are not sophisticated at all, like kind of in the general space. We're sort of saying, is this answer a subspan? Like, is this named entity, which is considered the correct answer to the question, appearing somewhere as an exact string in my model's generation? And that's very poor and like just doesn't work that well. And all the models are quite close in their performance, and the error in that metric is very, very large. And so like a lot of work that we've done internally is trying to benchmark better. And poll is a thing that we shared because like we were sufficiently kind of like grumpy about some of the things like that, we thought we can share this is a contribution. It's not specific to RAG, but it's kind of like where it grew out of. So we wanted to basically build better metrics that allow us to judge correctness, for example. And we looked and saw what was out there, and there's a bunch of kind of quite popular open source tools that you can use to do RAG evaluation. They were not very good for what we were looking at, and so we thought, we better develop something else. And we looked at some of the core assumptions that people are making in using language models as evaluators out there in the world. And there is quite a core one, which is like, a lot of the time people are trying to do very sensible things. And they're saying, if I had an Oracle LLM, like it was perfect, what were the things that I would need it, like that, how I would use it to do an evaluation? And then they assume that GPT-4 is an Oracle LLM and you can just use it, or any powerful large language model is going to do that job well. But really what you're doing there is setting up an ML problem, and you're not doing the evaluation of that thing. So you have to evaluate your evaluator. This is the first thing. It's like, how well is my system working if I apply any kind of evaluation system that isn't just a very straightforward canonical metric from the literature, which is, you know, useful by consensus. If you're doing something new or you're using an LLM as an evaluator, you need to first understand the correlation to, like, you know, the actual gold standard evaluation, which is usually pretty close to asking 3 humans to do the problem, to do the evaluation. So like, until you've got your effectively your inter-annotator agreement between your LLM judge, your like model based evaluation, and your humans, and you compare that to the agreement rates between humans and other humans, you don't have an evaluation. You just have a thing that produces a number. So you have to do that. And then when you've done that, you can then start to compare different styles of doing LLM evaluation, because you can then evaluate your evaluator. And what we found doing that is that GPT-4 or like really, really powerful large language models were not always the best at this, counterintuitively, and that in general, LLMs being used as judges were worse than they could otherwise be. And that's the start of poll. The second part of poll was saying, okay, like, given we need to build an LLM evaluator, like automatic evaluation is important, how can we do this better? Inspired by what we're seeing with these kind of self-preference things, where like large language models are pretty good at detecting their own outputs or their model family's outputs, and they may prefer them, they may disprefer them, but they know that, like, they recognize themselves. And so you say, oh, what can we do to mitigate that? Well, we'll just use like 3 different models. And if you ensemble them, not only do you get the benefits of, generally when you ensemble models together, you tend to get a better model, but you're also specifically mitigating the risk that command R might prefer command R, or Haiku might prefer Haiku, or GPT 3.5 might prefer 3.5. You like smooth that out. And then you just see empirically it works really well, and that ensemble of smaller models often outperforms GPT-4 or Opus or big models,
And cheaper, because small models, you can do it in parallel.
Cheaper and faster, yeah.
But you said some really interesting stuff in the paper. I mean, the first thing you said, just as you did now, is that, GPT-4 is spectacularly wrong some of the time. And you thought that might be because it's over-reasoning. It's actually like it's being weighted too much by its base training. And you spoke about, the annotator bias, the model bias, the style bias. So there's all of these problems. And it really does make sense to kind of like aggregate over them. But you also said, well, a really interesting thing to get it closer to what human evaluators might have done is look at some kind of correlation between something like LLM Cicerina, because you actually have examples there of human, decisions, and you can kind of look at some kind of correlation between them. You had this kappa metric, right?
Yes, Cohen's kappa. It's a metric, people use it, but like it's hard to interpret. So it's more like one of those things, like it's hard to know what a Cohen's kappa of 0.7 is, but you know that a Cohen's kappa of 0.75 is better than 0.7. But like for different problems, it doesn't necessarily compare, but it is a way of comparing. It's a statistically more vigorous and better way of comparing than, say, just binary agreement rate. It basically corrects for the background. We're just using this Cohen's kappa thing. It comes from annotator agreement, kind of canonical scores. If you have more label spaces or more annotators, there are other ones that you pick off the shelf, but Cohen's kappa is sort of the simplest one that people tend to use for inter-annotator agreement. And we kind of view this as like, we have evaluators, we have like annotators, and sometimes there's annotators as humans, sometimes they're models. And so you just have to compare how different ones compare to each other. And so we're using that inter-annotator agreement metric there. But you're coming back to the GPT-4 and the poor performance you sometimes see using it as an evaluator. It's very unpredictable about whether it will be great or bad, and you can't know from first principles. You can maybe like do some kind of you can think about it, maybe come up with some estimate, but until you get the humans to evaluate your problem at least a bit, you don't know whether GPT-4 is going to be really good at this or really bad at it. And in the case of one of the evaluations we were doing, it was particularly weak, even compared to GPT 3.5 with the same prompt and all the other models that we were looking at. And so what I did is, like, you know, one of the last things before we like threw it out into the world was sat down for like half a day and just did some like prompt engineering to see what it would take to get GPT-4 to reach the same level of like performance on this task as GPT 3.5, which is kind of like a counterintuitive thing. It's like you're almost always doing the other way around. And yeah, it turned out that like GPT-4 is more sensitive to the prompt structure than other models were, the smaller models were. It also turns out that because the task involved these factuality things, like these are questions that are annotated in 2019, I think, and the world's changed a fair bit. So they're saying like, when does the next season of insert TV show here come out? And the answer was, you know, based on some time. And the task we were doing is saying, here's a reference answer. Does this model generated answer match the reference answer? And the LLM's just to say yes or no. And what we think was going on was GPT-4 was knowing that the answer to the question was different now and being confused and upset about that. And it has, you know, all these conflicting kind of signals in its reward model training and its post-training that it's not really supposed to, like, it's supposed to be smart and like work well in other contexts maybe. And I think what it was doing is getting a bit confused between the consistency between the answer and its prior beliefs about the world.
Yeah.
And what it was being asked to do, which is say, is this wrong answer the same as this wrong answer, according to like where the world is now, but at one point these were two correct answers. And it was like, had this like difficulty in its head. And so you could like cool that down a bit by saying, this is just a case of semantic matching. Don't use your facts about the outside world and don't overthink this. And that, and a combination of those kinds of like styles of things to like adjust the instruction you gave the model when it was doing this judgment thing, managed to get it up to about the level that GPT 3.5 was at with the sort of standard prompt.
Yeah.
It's a kind of interesting reverse scaling law in a case like that. These things are kind of rare. This is one thing that Ethan Perez, that one of my collaborators, used to talk about a lot, like when he moved to Anthropic, where he is now. A couple of years ago, they held a kind of competition to find reverse scaling laws, things where smaller models were better than bigger ones. This feels like it's kind of like that, where you want the model to do something quite simple, but it's too powerful and it's worried about more subtle behaviors, and so that's kind of getting in the way of it just doing the straightforward, simple thing.
Yeah, it's a little bit like the no free lunch theorem, but during the process of training, you're kind of running this whole sausage factory, and presumably you're then using that to fine-tune the base model. So the base model has internalized all of these judgments. Is that fair?
Yeah, kind of. Like, we collect a lot of demonstrations of what like good examples look like. That's sort of at the SFT step, or thinking of it a bit more in an RL way. We have quite a lot of like gold annotated trajectories effectively.
Right.
So for imitation learning.
Yeah.
And then we also collect a bunch of preference pairs that might be most of this is verified by humans. So like the cleanliness of your data is super important, both for supervised fine tuning and for preference. So you can either defeat this with vast scale, or you can defeat this with moderate scale of your data, but with like very obsession over cleanliness. And so we go the cleanliness way because of the budgets. It's much more, it turns out to be much more efficient. If you look at, say, like LAMA 3, its preference data set, it's like some millions, right, of preference pairs that they annotated. Number one, is very, very expensive. And number two, there will have been some sacrifice of the quality of that data. And so there'll be some amount of it that's not the right way around, or is subjective. We work very hard to make sure our data is all very, very good. So we tend not to do too much synthetic training, i.e. what I mean there is like apply all these metrics that we've talked about, these evaluation metrics, and train the model to optimize them. That is stuff that we're interested in doing, but we know is not the most efficient way of improving the model. That's the cherry. And we're still like in the cake. And at some point we might, do some very, very last minute polishing of the model with some like online RL with using these metrics as, like optimization, but usually we're carefully thinking about distributions, annotating them and training those into the models and being very careful with how we train and ablate the model to be good with those sort of things. So there's a lot of complexity to what we do, but that complexity is more operational than technical at this point.
What you're describing at the moment, as I understand it, is you've rolled out these processes and you've baked it into a model, and there are more interesting variations of that where you actually either use the human in the loop as an agent, or you have an auto judge, which is an agent, and these things are post hoc running after.
Yes, you can kind of like say, oh, like, that wasn't good, and you can like force it to go again, or you can you can kind of critique it online. I'm quite interested in human AI collaboration. So like the next phase of this is going to be like you have your work assistant to do research work or like knowledge work, and not unlike code co-pilots, like we don't know exactly the correct surface form that's going to take, but we also know that we want the model to take demonstration, take instruction, improve fast learning in the loop, this kind of thing. But even something as simple as like taking a model that works quite well, like our React agent. So React is just a way of doing like chain of thought over several hops. So that's how a lot of these models work right now, is this very simple thing where you just say like, I'm going to get a model to sequentially call tools, and it's going to do that by first generating a plan, then generate the tool API calls it wants to take, and then you call the model again, and it like looks at its observations that come out of its retrieval systems or other tools it's connected to, and then decides whether it's time to answer directly or whether it's time to do another call to the API. And so it kind of looks like in situ, generates a thought or like a plan, calls some tools, generates another thought, calls some tools, and then at some point it reaches this terminal state and answers you, generates an answer. They work quite well, but often you'll like ask it something and it will get the premise a little bit wrong, and it will start to go, and you'll be like, oh no, stop. If you just edit its plan a little bit yourself, you can very quickly steer it to do kind of what you want. So there's some quick fixes there, but like generally, it's like how you collaborate with the research agent to like quickly get it to do what you want, and how that process, like it can learn like to work with you quickly. To me, that looks like something like a version of in-context learning, where you like take the feedback online that it's giving, that you're giving it, and you and your agent get some like quite fast synergy based on just working together. I look a bit at like different ways of giving effectively like demonstrations to the model. Like a lot of people are excited about getting models to power browsers or power your desktop and that kind of thing. Like, I'll just record me doing a workflow and get a model to do that. I don't think that's all of it. Like, I think that's missing something. I'd make the analogy there between, it's like any kind of automation. Like, we could make an automated train, or we could get a self-driving car. And a self-driving car is a much more challenging thing. But if you don't have a road network yet, do you really need to solve the self-driving car problem? Or could you build a road network that's more effective, right? That you don't have to design around the human. Like, does the LLM and the human who are collaborating to do knowledge together, do they have to share the same experiences of like what that looks like? Like, how many kind of concessions are we making to like the human UI and desktop? What kind of way should an LLM experience the things it needs to interact with to like make the human more efficient? Like, often that could just be APIs. Like, it can directly interact with an API. It can interact with the browser, but it may be slower, worse, more error prone. And so I'm kind of like very interested in this human computer interaction problem right now, and skeptical that just getting LLMs to power browsers or power the desktop is the right way to do things. It just feels very slow and inefficient. It's general, but like not quite there for me.
For me, like, understanding is about reconstructing the intention of another agent, so the reason why we have this divergence in multi-step tool use is because it didn't really understand what you wanted, and it very quickly, especially if you have like, by the time you're on the third step, it's going in a completely different direction. And then you need to have a really cool UI where you can say, no, wait a minute, that's not what I wanted you to do.
We make assumptions that it's an agent that like you go and task to do things, but it's a bit more collaborative than that. I think it's going to be interesting to like see how we work through these things. Like, that's a lot of what our team are gearing up to do, is a lot of this thinking through what those those collaborative systems should look like for kind of productivity, and not getting the LLM to get in the way too much, but still help you and automate things that you find slow or you want to do quickly. The same thing happens with humans to some degree. Like, I'm a manager and I've got like a really great team, but it's often like maybe I'll communicate something I want someone in our team to do, and then we'll come together next week and they've done something totally different. And that's on me. I thought I explained myself pretty carefully. So like, even like to autonomous agents who are pretty powerful, like me and someone in my team, that transfer of, like what you were saying in terms of like getting my intention into them and getting them to operate on it is like fraught with difficulty, even for like humans to communicate that kind of thing. So yeah.
I had early access to GPT-3, and it was still at the point where, I was kind of saying, I think this is a bit of a parlor trick. It's not really. There was a famous database example from Matt Brockman, and he said, "Oh, John is in the database. I'm removing John from the database. Does the database have John in it?" And it appeared to be working. And I was like, "Come on, guys, this is bullshit. Stop doing it." But the amazing thing is that there was a community of people who, even though it was very just random, sometimes they could see something in it. They could see something interesting.
The vision there is actually quite impressive. I saw it as a target for fine tuning, because that's a paradigm that you would do, say, BERT, and even models before that, you would say like, all right, the paradigm's going to look something like this. Like, we get great representations and then we fine tune it to do something. But the fact that you could do this generation without anything, without actually changing the parameters, and the fact that you could like prompt it with this in-context learning stuff. And I think like one of the great things that OpenAI did in GPT-2 and GPT-3 was talk about this like unsupervised intelligence that was coming out, although the ability to do tasks in a different way. The orthodoxy would have been, we trained GPT-2 and then we fine-tuned it to do a bunch of stuff and it's great. That's what they did in GPT-1. But they were like, now let's move it along. We're just gonna like give it a question as a textual input and see if it can generate an answer, or the TLDR stuff. They were like, we're gonna try and like fool it into summarizing something based on some common patterns from pre-training. Yeah. And then in GPT-3 with the in-context learning stuff, it's like, well, if it's a language model that tries to predict the next most likely thing, if you give it a very predictable like pattern of sequences, can you then like train it on the fly with like it reading kind of on the fly to do things? They were like, really interesting, like novel takes on what could have otherwise been a case of like, we just made this really powerful model. You can use the same techniques that everyone has been using to achieve great results. I kind of think it's great that they went the other way and said, like, let's move this on. And this is kind of like what is enabled. I've not seen too much of that from the big labs since. Usually it's a case of like incremental improvement phase, where the increments are quite fast and like the models are improving a lot, but the paradigm hasn't changed for a little while.
Yes, and I think we'll get on to how that might change. But just to kind of recap, so we have the base training, and then there's fine tuning, and then there's this whole domain of preference steering, things like RLHF, and that's kind of saying, I want you to talk like a conversational bot, and I want you to be precise, and I want you to adopt this tone of language. So we're kind of shaping the distribution. But then the in-context learning is the interesting thing. So you can do that, or you can say, you're a chatbot. You are just like Donald Trump. You behave in this way. And you had this genius idea, which is called Retrieval Augmented Generation, which is based on this idea of in-context learning, which is putting instructions in.
It's quite funny because at the time we didn't think of it quite in that way. We came out of a reading comprehension and like question answering space. So some of the things that I used to do before my PhD, the company I was working at, Bloomsbury AI, that became the seed for the FAIR London lab, was working on open domain question answering. And so there's a very long tradition of having a corpus of text and needing to like answer questions based on it. And a very common way that you do this is via like retrieving like the most relevant pieces of information and doing some transformation on it. And so for the longest time, there were these like tasks that you'd study in question answering NLP called reading comprehension or extractive question answering, span-based question answering, where you would train a neural model to take a paragraph of text and you would point to the beginning of an answer within that text and the end of an answer within that text. So, and that's kind of closed world, be one paragraph, one question, and you'd extract like an annotated answer, and you'd train a supervised model to do that thing. Where we were coming from was that kind of world. And if you wanted that to be more useful than just answering a question over a short document or paragraph, you would hook up a retrieval system to that. And so you'd have a bunch of paragraphs, you'd have a question you wanted answered, you'd retrieve from it, get a number of paragraphs, and from those paragraphs you'd use your neural model usually to extract these specific spans, and it would literally say point to the start, point to the end. That's your answer there. And you'd produce these like collections, and then usually have some re-ranker or something. Like that's how a lot of like question answering systems were working. There was some interest in how you like train these models end to end in a way at the time, where you say, okay, I've got these systems, I've got this retrieval system, and I've got this like question answerer, and I'm going to train them end to end with some like fun latent variable like learning models, quite straightforward from a kind of generative story perspective, but like, you know, quite difficult to get them to work in practice. And there was a lot of this kind of stuff going on at the time. Then there were the introduction of these models that could generate text very well.
Yes.
From one perspective, one way of looking at what we were doing was saying like, okay, let's, instead of doing this span extraction thing, wouldn't it be nice if you could just have a model that instead of extracting an answer, just generated the answer that you wanted straight away? And so we didn't really think of it at the time from that perspective via like from the in-context learning way of doing things. But like it turns out there's kind of equivalent. That said, there is a whole different line of work that we were doing at the time based around like knowledge in language models. And so these names are kind of hilarious now, but we had a probe or a way of like measuring just relational knowledge that like language models like BERT or simple GPTs had. It was called the LAMA probe, which is kind of hilarious because it was, you know, years before LAMA. And so there what we were doing was saying, okay, like I'm just going to give a language model, like the president of the USA is blank, and see what like it chose to put in there. That's kind of like zero shot prompting. And then we had a different work called Alpaca, which is again kind of funny because that was before any of the famous alpaca now. And what we were doing there was saying, okay, does the model get better if you give it a paragraph beforehand? And that's this like in context learning idea. And we saw that on that very simple LAMA probe, it got way better. And so we had these two separate ideas saying like, what if we wanted to have a generative open domain question answering model? And we wanted to like extend these alpaca ideas. That's the kind of two bits that we put together into this first Retrieval Augmented Generation paper. The reason I kind of explained it from those two angles is because there was two kind of groups of people who came together to do this stuff. Like I was working on the alpaca stuff. I was also working with Dao and Ethan. So Ethan's the other first author on the RAG paper, Retrieval Augmented Generation. And Dao was the last author along with Sebastian, my supervisor. And so we put these two groups of people together, the people who were like, what if we did this open domain question answering system, but generative? And we took the in-context learning, I guess, as you say, like paragraph reader, LLM improver kind of thing. And we were like, okay, let's just design this thing that, you know, you hook it up to an unstructured source, you give it a prompt, it will unsupervisedly learn what relevant information is from your information. And then it will generate you a free-form answer using this kind of in-context learning thing. But we're going to fine-tune the system end-to-end, and we're going to try and target, like at the time with the RAG paper, it was quite an empirical focus. Like we wanted to get good results on benchmarks, and that was our kind of goal with it. So introduce this framework, this like way of looking at things based on these very new generative models, like generative language generators. And that's where it kind of came from. So it was kind of just like a zeitgeisty thing where you just had these two groups put us together and did this thing. And for a long time, everyone was like, hey, that's quite cool, but didn't really like, it was just a paper in the space. And then I guess about 2 years ago, people started to use this acronym in conjunction with like large language models and hooking them up to retrieval systems in a more general sense than what we meant when we first like wrote the paper. So like the Retrieval Augmented Generation paper is a way of doing RAG, but it's quite different to what a lot of people do these days. And it's become this term or this way of referring to a very general set of solutions to the problem of knowledge and language models, which is kind of like funny from my perspective, because like really the first paper was just a paper in a line from like lots of different people. And there's lots of like similar systems, almost the same kind of thing, maybe without this generative aspect, because really those systems only appeared about 2 months before we put the paper out. But yeah, lots of people would be like, "Oh, he didn't invent RAG," and I don't claim to. People tell me I do a lot. But yeah, it's just like a zeitgeisty thing. You know, lots of people having the same sorts of ideas at the same sorts of time.
Yeah.
And I think we just gave it a 3-letter acronym that people can ascribe, you know, easily refer to that like group of ideas with.
Amazing. So I guess we should split it into the architecture bit and maybe the UX bit.
Yeah,
But
yeah, sure.
you're describing, as you said, a collection of possible architectures, and a significant component of it is information retrieval.
Yeah.
And I guess the complexity here is, you know, a person implementing RAG, they might be in an enterprise and they might have knowledge stores, semantic indexes, blobs, SharePoint, blah, blah, blah. So they're kind of, they're hooking in all of this stuff, and they need to have relevant scores and so on and so forth. So just the information retrieval bit is already really difficult.
Very tough. Yeah.
And then they do the AG bit.
Yeah.
And the two things are kind of, from a UX perspective, they're compounded together. So now I see a bunch of augmented generation.
Yeah.
What could possibly go wrong?
Yeah, exactly. I mean, there's so much there, and I like the way that you broke that into the two parts. So now if I describe what my team does, I would say there's sort of two broad parts. There's tool use, which grew out of like using an information retrieval tool. So we've kind of abstracted a little bit away, so you can do more sophisticated types of retrieval, or just cool things that aren't even retrievers anymore, but are kind of like producers of information that you might want to inject or like get. And there's the tool use part, and then there's the what we call grounded generation, but like you can think of augmented generation as being a similar thing. We call it grounded generation because of the way that we effectively annotate and think about it internally, using this concept of citations, which maybe we can talk about in a bit. But there's the tool use part. That's kind of hard. There's lots of things that can go wrong. Even if you abstract down to the very simple things like, okay, my tools are only retrieval systems and they only take natural language queries, still kind of hard to figure out, given an input, does it need retrieval? Does it not need retrieval? If it does, what is a good search query? Am I using a keyword-based retrieval system? Am I using a like dense retrieval system? They will prefer different types of surface form of queries. Is this something where I need several queries? Often there's things where you have to do these parallel retrievals to like get the information to fully satisfy your information need. In the tool use literature, this is called parallel function calling, which we kind of accidentally did without thinking about it too hard, but it's like a bit of a trendy thing now. So there's this tool use stuff, and then you have this very difficult problem of saying, okay, I've called my retrieval tools and I've got all these documents out, and now I have to like squash them into my second call, which is where a lot of things get even harder. And the reason we kind of think about these things separately is because that's a sort of difficult challenge in and of itself, and sometimes you want to do this grounded generation, this augmented generation thing without the tools. You can imagine like summarization is an example of this, where you say like, here's my big document, summarize this. And you have to inject your document into the LLM in a very, very similar way to you do with like reading retrieval results. And so like this is a sort of broad class of problem I think of as like, you've got some things to read and you've got a task that you're trying to do, and how you generate a good response there, super hard. There's a lot of different factors to think about. You have to think about faithfulness. You have to think about, say I have a bunch of documents. The model has this inherent tension between its own prior belief about the world, which usually comes from either pre-training or post-training, and the documents that it's reading on the fly in context. And they may be in tension, they may be in conflict. So temporal stuff is a key, like a very common way this comes up, where that President of the United States thing is the usual, like easy way people think about this. Like that changes over time. And the model may think that it's Donald Trump, but it's actually Joe Biden now. And so if I give the model a document that says the President of the United States is Joe Biden, and then I ask the model, who's the president? It has this inherent tension. And so the model has to be like set up to do one or the other. There's interesting like safety or philosophical questions that come in there as well. Like let's say I'm internet augmenting and I'm asking about elections. And that's a key place where you might get bad actors who might make easy to retrieve information that will confuse or like break some of these systems. And it might happen by accident as well. So like a lot of the things where there's been in the news issues with, say, Gemini producing some quite strange answers, that's often happening because of a misinterpretation plus faithfulness kind of problem. Is like the model's saying these quite ridiculous things that without the retrieval augmentation, it probably wouldn't be saying, but it's being kind of like injected in some ways, or it's like other things are going on where, yeah, you get these very strange results that aren't great coming out of it. And they're kind of illustrating the challenge of this augmented generation step. So if there's faithfulness problem, you also have additional issues that are kind of like less obvious when it comes to augmented generation, where you want your model to stay producing a nice, pleasing response for usually in a chatbot situation. And so you want it to say like a nice, fluent response. You're also counterposing that against this faithfulness thing. And so sometimes it's not always a zero-sum game, but these things can be in slight tension, that it's often difficult to balance faithfully representing the information in your retrieved information versus writing a nice, high-utility response to a person. One of the tricky empirical things to get right is where you need to decide if a question is answerable or not. So you've got the retrieved information. Does it answer the question, or like the information need of the person using your retrieval augmented generation system? That's pretty tricky because the way things that come out of retrieval systems might be is sort of like partially extracted from their context, that usually just chunks of information from pages. So that's a very tricky like decision boundary to make as well. There's practical applications there about also like, is it worse for a model to sometimes respond where there isn't information in its retrieved in its retrieval stuff, counterposed with abstaining from answering all a lot. If there's going to be errors, which do you prefer? It's almost like a precision recall style thing. Like you can't always have 100% accuracy here. So would you prefer a model that refuses to answer more, sometimes be quite frustrating because of that? Or would you prefer a model that runs the risk of, as it were, hallucinating a response? And so these are really, really tricky things to like drill down and get right, especially when like you have to do already so much work to get to a point where the system is at the point where it even works at all. Like prompt engineering to get augmented generation working is really, really hard. And sort of what we do at Cohere is try and build like actual like prompt templates that the model has like very, very concrete like awareness of in the way that we post-train. And so there is a correct way, I guess, to do the prompt engineering there, and we'll template that for you using the API. And so you can avoid a lot of the startup cost associated with building one of these things. And so then the model kind of is familiar with the concept of a retrieved thing. It knows what that is. It knows how to deal with it. It knows that a bunch of retrieval results in a row, if I permute the order of those, it should have no effect on the model's answers, right? Like just because I take my top 10 retrieval results and shuffle the order, it shouldn't change the answer quality. But for every single LLM other than ours, it does.
Oh, interesting.
And we take steps to avoid that, basically. But we can only do that because we control the prompt templates. And so like effectively our APIs have a documents parameter or a tool output parameter that we can use to ensure the model doesn't violate some of these principles in training. At least when I do evaluations in other people's models, that's also hard because you don't necessarily know the optimal prompt template to render for the best result you can get from GPT 4.0, for example. Like I find it very hard to evaluate RAG systems and like know the true upper bound of like how good someone's models can be. I know it for my model because we put a lot of effort in, but when I try and do like a true faithful comparison, which is something I really care about, it gets very tricky. There's also other like interesting things that happen. Like what should you do if two pieces of retrieved information are in contradiction with each other? What should you do if you have like ranges of information? So let's say I ask a numerical question and I find a bunch of different answers for what that numerical answer is. These are all quite pragmatic things to work through, but they're things you have to like decide about how your language model should work. And they're interesting to kind of work through.
I mean, the picture I'm getting is that this is insanely complex. So there's this entire sausage factory, and
Yeah.
you've done some stuff, and obviously the customer needs to configure this quite a lot.
Yeah.
And one immediate observation is information retrieval is already, it's an interesting example in software, because normally when Microsoft or Google or whatever, when they build software, they're solving the hard problem and they give it to you via an interface and you do the easy problem. Whereas with information retrieval, if you're building an enterprise search system, it's actually harder than building Google.
Yeah,
And what
it's
I
very
mean
hard.
by that, and I'm glad you agree, what I mean by that is Google has like all of this statistically significant information. They've got page rank, there's this
Clicks.
like hypergraph,
Yeah.
they've got all of these head queries. They've got millions of people clicking on, you search for this, millions of people click on it. They've got the total number of clicks. They've got really powerful information. In the enterprise, first of all, you've got multimodal data, and you've only got really content metadata. You can't learn to rank, you can't learn relevancy from the users really, and even harder to do so with RAG on the top of it. So, and then you've got all of this stuff that you're just talking about. So I need to evaluate my system, I need to fine tune it, and it's so nebulous.
It's very tough. I think it's also it's one of those things where even if you try to evaluate it, you don't get a true sense of like what the problems that arise in application might be. You have to build the thing and put it out there and get alpha feedback from people trying it out to really discover where the problems are for your database or your kind of stuff. We can't easily know beforehand, so we can try and make the model as good as it can be. I don't work these days on the retrieval system itself. There's a different team Niels runs who build Cohere's embedding and re-ranking models that are very strong, but again they're based on semantic content rather than any kind of statistical usage or things like that. It can do things with metadata as well. But again, it's all based on getting the model to kind of not reason, as we talked about, but try and rank things based on content, the content of the information rather than how often it gets used.
Could you talk to that a little bit? Because you use the terminology, dense versus sparse retrieval, and I think what you mean by sparse, I think you basically mean an inverted index, like an old school
Usually,
one.
yeah. It comes back to Word2Vec in a way. We're going back to these same core concepts really of say okay, we can represent a document by the words that are in it, and that's usually how this stuff works. So that what's there in the document. We can either do that by recording sparse features, like the words, or we can do that by embedding the document in some way, or storing a representation that's comes out of a neural model or some kind of low dimensional representation of that. Those are the two kind of broad classes. And then if you do it with a sparse representation, that traditionally things like TF, IDF, BM25, these kind of things are basically based on, you just say, I'm going to break the document up into words, and I'm going to build very long, very sparse vectors that have a vocabulary size, and I'm just going to count all the terms or words that appear in my document. That's going to be my representation. And then I'm going to build an index of all the documents in there, and you build these efficient lookup systems, like you said, like an inverted index that makes it quick and easy for me to take a query, which is usually some words, and do the lookup to quickly find which documents have those words in them. There's a lot of finery that goes into the specifics of how you modulate the weights of the vector, the sparse vector. So is it just binary, this word is in here, or is it not? Usually you moderate it by how much more that word appears in the document than in the background. And there's decades of information retrieval research that went into that. That was the sort of primary way that information retrieval worked before representation models got good enough to build these dense vector models that usually either represent a chunk as a single vector, or now there's multi-vector techniques that kind of do it slightly differently. They're effectively just different ways of representing the information in chunks, either with a sparse representation of individual features or these kind of semantic spaces that you build and retrieve over in a kind of different way.
So with the inverted index, the good thing about it is you can essentially use a hash table.
Yep.
So you've got a constant lookup time, and with the dense version, because it's in some kind of a vector store, you've got like a log lookup time. But what I want to say though is, the good thing about the sparse version is specificity, and the bad thing about the sparse version is specificity. And like you've got, let's say, a high entropy word or something, so like a low frequency word. That's great. Boom, I've got the thing. But it doesn't always work that way. So what how do you contrast the two?
Yeah, if you ask a sufficiently generic or like surface form query, you often don't get what you want with a sparse index usually. Also, in the way that we've described the sparse indices so far, it's harder to learn from data. So sometimes we have data that allows us to know that like certain queries pair with certain documents, or we may be able to add those as like priors. And so initially, like a lot of the things around like the dense methods were in favor because you could train a model to rank a certain document very closely to like an embedded query or question more easily, or with more kind of power and like more connectivist kind of like thinking than you could with the sparse ways of doing things. They were a bit more powerful from that perspective. But yeah, like there are issues with the dense model as well, as like you don't get that specificity. So like it is sometimes harder with especially a low dimensional dense vector retriever. If you do put some like very specialized terms in it, it might not have the like representational power to like do that kind of very precise addressing. So usually in practice, a lot of the systems that are most performant are a hybrid. So you'll do a dense retrieval and you'll do a sparse retrieval, and you'll combine them and throw them through. What we do in a lot of my work, like in our team's work now, is assume a black box retrieval system. There's so much for us to focus on. We will assume a black box retriever, just try and deal with what comes out. And that might look something like there's a concept called query reformulation, where like we're trying to train these RAG models, which to some degree now we can think of them as research agents that kind of like go over several hops, but they'll like try a query, see if they find what they like, and they might not find it. They can reformulate. They can say, okay, that query didn't work, I'm going to try a different type of query that might be similar, but like I've added some words or I've changed some words, and try again. So you can repeat this like reformulation process.
Oh, wow.
Where you
it's almost like agential information retrieval. Sure. So there's actually a kind of iterative loop there.
Yeah.
Because I was going to say as well that another thing you can do is kind of query expansion.
Yeah.
And I guess that's even more relevant for sparse indices. But it just goes to show there's this huge sausage factory.
Yeah.
And it could be an agential thing. And before we move off retrieval, I think one of the biggest concerns I've heard from people is the sensitivity problem, or the recall problem, which is that there might be missing information in the results. So the language model will kind of, because there's this sycophancy problem that the language model will say whatever you tell it to say.
We'll fill in the blanks,
It'll fill in the blanks. It'll confidently say something is the right answer when it's missing the underlying information.
Yes, that's a great point. So that kind of, we can transition to talk about grounding and attribution and citation. They're all like different words for sort of the same thing in our view, that how we train our systems and how we annotate for our data that like helps us train our systems is that when we're doing this augmented generation step, the second step, the model generates its answer, and we ensure that all of our annotation, every claim that is made by the model, like something that can be recognized as like a piece of like a factual claim or like a piece of knowledge, we ensure that it is annotated with a link back to the retrieved piece of information where it comes from, or the several pieces. We're very, very fastidious about this. And we indicate to annotators that like unless there's specific instructions for the task that's going on, every single factual claim has to be attributed back. And that is the way in which we've kind of, over time, really built out our model's abilities to be very faithful and to avoid that sycophancy problem. Is like the model has a prior or bias effectively trained into it that it really doesn't like to generate things it can't then attribute. The way this works actually in practice is that we generate the text with these markers in it. So like these little citation markers that appear, like span indicators around facts. And number one, like as a user, you get the immediate like visual feedback, I guess, of like if a claim is being made by the model, you see, oh, there's no, like the model hasn't generated any citation spans or attribution spans around here, that's much less likely to be something the model could support with evidence. And therefore it's likely to be a hallucination. Even if there are like, you know, those markers there, it's less a sense of like, hey, this is like true. This is like something I can trust. It's more, I have a pointer that now lets me verify it easily. So I can look at and see, oh, like, here's this piece of information I want to believe the model has told me. Like, responsible operation of like any piece of technology or machinery is like, it's on you to take that information that you want to believe and sufficiently convince yourself that that is something that you should then go and make decisions about. We don't just say anyone can drive a car. You have to train yourself to drive a car. Again, with like online stuff, is like if you see a claim on an online like social media platform, you shouldn't just take it at face value. And the same thing with like an LLM producing an answer from a retrieval system. But what we should do is design the way the retrieval augmented system works to make it as simple and straightforward to go and verify that information and trace the information trace back to like where it comes from. And that's what these spans are about. So you say the spans are there, like it's saying this information comes from document 1 and document 2. You do then, if you want to make a decision based on that, you should really go and look at document 1 and document 2 to make sure. But we at least tell you it's from document 1 and document 2. Whereas if a model's just generating this answer directly, it's much, much harder because you may have 30, 50, 100 documents to look through, like pages and pages of stuff.
Yeah.
And that becomes more of a pressing concern with long context. So as we get models that can process more and more and more tokens at one time, this like grounding thing of saying like, I got this info from here becomes very important. Otherwise, it's just kind of reverts all the way back to just being an unaugmented model because there's just so much stuff there that it's effectively, you know, not too different in terms of just like asking the model to do something based on its sort of parametric.
So two pieces on that. You said first of all your annotators. So the interesting thing is that the command R model is actually specifically trained to do RAG.
Yeah.
And you've know, got a whole bunch of annotators and you've said this is what good looks like, and that's why it's better for RAG than other models.
There's specific large amounts of annotation in our post-training data, and our supervised fine-tuning step and our preference steps to make it good at this. It's not just the sense of it like it being good, it's also like the sense of these built-in citation mechanisms. There are specific prompts, and they're documented on Hugging Face. There's links to them effectively like that show you what those prompts look like, that if you use those specific types of prompt, the model will kind of switch into a RAG mode and will reduce its sycophancy by just prior and bias. And it will switch to something much drier, much more faithful, much less creative, but much more appropriate for a system that's always going to be augmented by retrieved information or information that's augmented from tool output. Same thing with tool use. Like there are special prompts for tool use that are documented on the Hugging Face model card for Command R and R+, that if you use, you'll get this intentional behavior.
Surgical.
Yeah.
Yeah. Could you comment on the UI in general? Because I mean, maybe like we could look at Gemini or Perplexity as an illustrative example of RAG. So you do a search, you have a load of results coming back. I mean, in the olden days, I would go to Google if I'm planning a holiday, and I would kind of have a whole bunch of stuff in my mind. I'd have different tabs open.
Yeah.
And now that entire kind of cognitive tree has been compressed into a load of text results. And on Gemini is quite interesting as well. So when it generates code, you can actually hover over the lines of code and it will tell you, oh, this came from GitHub, and you can go and look at it.
Yeah.
And that kind of makes it a lot more transparent. But part of me is also thinking, like in the 1980s, we used to have to use command lines to talk, we used to have to use text to talk to computers, and there was this UI revolution, and now it's far more structured. And like, do you think, is it a good thing to go back to a textual interface?
I think in general, there's like very interesting questions to ask about like human-computer interaction and what like language models and these kind of systems mean for that. We do two things. We think about how we can make our RAG models work generally well, and how we can make them work very well in specific user interfaces or in specific UX. given that we're now making these research agents, agents need an environment to operate in and not necessarily a space of potential environments. And so it's quite hard to make a really good agent unless you say, here is the UI that it operates in, and these are the rules it should follow. And so like we do think quite carefully about where is the destination for our language model acting as an agent being, and like how can we like optimize for that like fully. So like say like we have at Cohere the ability to like control the entire training stack all the way from pre-training to the final thing that you see. We can take advantage of that to some degree to make something very, very performant in a specific user interface or UI. The specifics of what that UI should look like, I think is an open question, especially when it comes to like getting things that are useful for people to increase their productivity or like feel that they're augmenting themselves and not just smashing stuff into a fancy search bar. Often it comes down to like, not just what should the UI look like, but also things that are critical for this to be useful. Like certain parts of the system need to have very low latency. That will affect a bunch of like design decisions about like how the agent should work, how the LLM inference should work, sizes of models, the trade-off between the size and the quality of the model to enable like the best thing to help you like get your job done faster.
Tell me about your story. How did you end up at Cohere?
I'm a trained synthetic chemist, organic chemist, but I kind of didn't really enjoy the practical elements very much. I enjoyed the maths and the physics of chemistry. And in my fourth year, the master's year, so I ended up in this kind of research master's working in a chemical informatics group. I was working with like a great professor, Professor Jonathan Goodman, and he kind of just said, hey, do whatever you think is interesting. But what I think is interesting is trying to understand things about chemistry from the chemistry literature. And so what we did in that project back in like 2014, 2015, it's like quite a long time ago now, I guess, was first collecting a big corpus of chemical literature, so like abstracts of chemistry papers and some small number of millions, I think it was at the time. So I wrote these scrapers to go do that stuff and then trained like a big simple algorithm on it called word2vec, which is quite famous. It's like one of the early interesting unsupervised NLP algorithms. So just sort of trained up this model, and then we took this model and I collected the word vectors for the chemical elements that this algorithm had learned. So word2vec is just a word embedding algorithm. It tries to build vectors in a semantic space for words. And so what I did is clustered the chemical element word vectors and visualized them with a few different methods. One of them was t-SNE, others were some force-directed algorithms. But the thing that like really amazed me is that even back in 2015, this algorithm, when you did this clustering of the elements, they clustered in such a way that they reproduced the periodic table without any kind of like explicit instruction or knowledge. It just had like read the literature and had discovered the periodic table within it. And literally like the noble gases were in one cluster, and then the non-metals, and then other types of metals, and it all kind of just made semantic sense. And that was like crazy moment for me that I was like, oh, this is amazing. I want to do this. And yeah, I kind of then quite quickly, wanted to find somewhere to work that I could do more of this work as a research scientist, working, always at this intersection of knowledge and AI, and thinking about like how we can use NLP systems to access and leverage knowledge, manipulate knowledge for like the kind of applications that humans find useful and we can learn things from. And then, yeah, I think I wanted to do something a little bit more long term. Like I found like the research loop at the time would last about 3 months. You'd furiously write code and you'd experiment on something, and then you'd write your paper and it would kind of be over, and your research arc and your kind of research journey and your body of work would grow. But I never felt that we were like building something in the same kind of way, and I kind of wanted to do that. So yeah, like moved to Cohere and built the team for RAG and tools, and here we are almost, I guess, 2 years later, talking to you.
Amazing. I take it Ed Greffenstedt from UCL as well, right?
Yeah.
And he introduced me to Minchi.
Yes.
Minchi is a legend. I've had him on the podcast twice. The first one was actually the most downloaded audio podcast we've ever had on the channel. I think even above Noam Chomsky.
Wow. So, that's great. That's a badge of honor. Yeah, he's amazing. I haven't seen him for a year or two now. But like, yeah, we used to hang out a bunch because yeah, he was a fair PhD student, one of the smartest people. Like he's so sharp and like he expresses himself very precisely as well, a bit like Ed. Yeah, great guy.
I know. I'm really happy that I got the scoop on Minchi because he's the perfect guy to interview because he's just razor sharp, amazing communicator. But a couple of things on what you said. So my co-host Keith, he has a PhD in organic chemistry from MIT.
Oh, cool.
And the transferability is insane. I mean, he's a god of Bayesian analysis. And he kind of, cut his teeth when he was at MIT. And I mean, even things like bioinformatics, when I did that on my undergrad, there was lots of sequence modeling and, Needleman-Wunsch and, like all of these sort of like approximate multiple sequence matching algorithms.
Yeah.
So there's loads of computer science in there. But you started talking about Word2Vec by Mikolov. I think that was 2013 was that algorithm out. And that's a really interesting place to start. So how does that algorithm work?
I think when it came out, so there's different lenses to look at like how that algorithm works and how it connects back to algorithms before. The broad idea of these algorithms is like you say, I want to learn a representation for a word. So I want to be able to embed this word in a meaningful space where like words that are more similar to each other cluster together or like exist closer together in the space than words that are more like distant from each other. The core idea behind a lot of these is like a word is defined by like its use in a sentence or use in language. And so what you can kind of do is say like take a word and try to predict what the nearby words might be. Or equivalently, take nearby words and try and predict what the word in the middle might be.
Yes, a word by the company it keeps.
Yes, exactly. Yeah, that's the kind of.
Is it by Good? What was the name of the guy?
I'm not sure who it is. It's definitely a linguist from like from early on. Right? I've heard that that repeated, and so effectively like Word2Vec. There's different actually ones within there. There's this one called a skipgram and a continuous bag of words are the two like implementations of this. It's actually very similar to masked language modeling, like the kind of modeling that's used for. They've fallen a little bit out of favor now, but like BERT and models like that, where you effectively predict what the word might be from its neighbors. It's just not doing it contextually. It's just trying to say like we will learn a word from all of the places it gets used, and it's going to be a representation effectively of all the words around it. And if you do that, it turns out that the optimum that you get is pretty powerful at describing what a word means. And so if we went back to the chemistry example, it's seeing chemical elements appearing in these abstracts, and the words around it are similar for chemicals that are similar. And so if you do this thing and you take the chemical words, what you end up with is these embeddings that have like just naturally learnt to be similar for chemicals that have similar chemical properties, because we write about chemicals that have similar properties in the same kind of ways. And so it's sort of like a distillation of the knowledge, really, a kind of just way of representing that knowledge. It's just really, really nice, unsupervised kind of thing. The other kind of way of looking at this in a kind of more technical perspective is like a lot of these word embedding algorithms, and there was like a very big kind of flurry of interest after you could see that, say, Word2Vec could do some like simple like word analogy tasks. There's the famous like king, man, and woman and queen, I think, analogies. And there was like a whole like zoo of these models that came out the year after that, looking at like, what can you do to improve this, or like, what are some like refinements. But if you actually like look back as well, there's like algorithms that almost do exactly the same thing, but weren't done at the kind of scale or like with the same kind of framing. And so a lot of these all end up kind of being imagining a very big word by word co-occurrence matrix. Columns equals like number of words in your vocab, rows equals number of words in your vocab, and you just build a big sparse matrix of where words co-occur within a certain distance of each other, and that's a very big sparse matrix. And if you do a decomposition, so like factorize that into smaller dense representations of these, so like word by dimension and dimension by word, and if you multiplied those things together, would you recover that sparse co-occurrence matrix? A lot of the algorithms end up being mathematically like an approximation of that factorization. So you can kind of think of it like that word vector is trying to be a kind of low dimensional representation of the co-occurrence matrix, of like literally trying to predict what the words that are nearby would be.
So it's very, it's almost analogous to collaborative filtering. You know, where like you might have Netflix and you have people and you have films that they like, and you've got this big sparse association matrix. And
yeah,
then,
very similar. Like,
yeah, and then as you say, you factorize it. I think there was a glove algorithm for word embeddings which kind of did it entirely, and then you can think of the Mikolov type algorithm as being like a kind of online version of that, where you kind of batch through the data.
That's exactly it. Yeah.
But the actual algorithm itself, I guess it had like 2 inputs. So it was like a sliding algorithm, and you would have, is it a neighborhood or adjacent words, and then it would learn some kind of intermediate representation.
Yeah, for word2vec, stretching my exact knowledge, and there were like 2 different ways of it. But yeah, effectively you'd have this traveling word window, and you'd like slide it over your big corpus, and you'd say, right, I've got the word vectors for this window, and I'm going to try and use the outside ones. I'm going to sum them up, and I'm going to blast them through a linear layer, and then I'm going to predict the middle one. And you're just going to see how similar those 2 things are. It's like the middle one that you've stored, is that close to like the sum effectively of the, with some transformation. You can also throw in like neural networks at this point if you wanted to like do a bit more transformation. You're just trying to basically make the aggregation of the surrounding words be as close as possible to the word vector that you've got stored for your middle one, initially starting from random, and then over time you optimize and you do gradient steps, and you just repeat this algorithm again and again. It's just an optimization thing, like not unlike a lot of modern NLP. And yeah, it's just like the beginning of these kind of like, distributed, continuous NLP things.
And to kind of touch on that, so I mean, it's interesting that it's a dense, continuous vector. And like the Netflix recommendations thing, it also has the ability to fill in the gaps. And that's a kind of generalization. So that means in situations it might not have seen in training, it could actually make some inference. And it's a highly dimensional space as well. So it's kind of representation learning where different dimensions might represent different things. And the algorithm, when trained in this way, because these neighborhood patterns exist in the corpus, it'll kind of fill in this information in the representation.
Yeah, because it has this like relatively low dimensional embedding it needs to make from this high dimensional space. It kind of like forces it to be quite efficient in a way with like how it's observing like the things, and like it has to like decide the best way to represent this sort of information bottlenecky kind of thing. And so like it's going to combine features that correlate in the high dimensional space so that it can like, you know, save some representational power. And like that's how you kind of learn. You go from this like super high dimensional sparse thing, and it sort of summarizes, if you will, like this information into the lower dimensional spaces, and they might be entangled as, you know, like the actual like meaningful dimension of variation for some concept that we'd recognize might be spread across several dimensions of the actual word vectors you end up learning, but there'll be a transformation where you can kind of find it. That's kind of like the magic of this stuff, is like the representation learning forces very sparse information to be represented by something like simpler and more summarized. You can make an analogy to how large language models work, even though they have very large hidden states and they have lots and lots of parameters to do it. It still pales in comparison to the amount of information they're trying to represent.
I remember when BERT came out in 2018, so that was like a kind of a masked encoder model where you would kind of like mask out tokens in a sequence, and it would give you really good representations.
Yes, it's quite interesting that we started talking about word2vec. It's basically the same idea, except if it was trying to make representations of that specific word in that specific sentence or like paragraph or context. And so you have to like, rather than just hey, here's my static word vector, you have to have a model that like takes as your sentence as input and then like embeds it on the fly effectively to get you your like contextualized word vector, which is unique just to that sentence. And then you've got it, and it's very like a very powerful representation that you can then go do tasks with. The first GPT came out roughly the same sort of time, but it was just a different way of, like, you could think of this generatively, or you could think of this as like a representation learning thing. It's like, what are we trying to do? Predict, generate stuff, or are we just trying to like get like good representations of language?
So BERT was a bidirectional encoding scheme that learned representations, going forwards and backwards.
And backwards, yeah.
And GPT was different.
Yeah, left to right. People obsessed about this quite a bit, like I did, other people did, and like thinking that this like bidirectionality is very important for like being able to like get a very rich representation of what the language is. From an empirical perspective, that's less of a thing these days. Like a lot of the way that we use language models now, you're not taking the representations from early on and doing stuff with them. You're prompting the model to generate something later on. So like you always get like a full attention on what's happened, and you don't necessarily often have to look forward in time very much. Although like there's the whole like text diffusion stuff going on at the moment, which kind of is a little bit different, that you might, rather than generate sequences out token by token forwards, you can just generate the whole thing a lot and just kind of iterate. This non-autoregressive text generation was a big thing that people were very excited about, seems to have gone away and now is starting to come back again.
But on that, because that's a really interesting inductive prior, which is, first of all, there's the locality prior, which is that, we're interested in things in the vicinity. But then there's this kind of prior that says, I'm only interested in things before, not in front. Why would that work?
When you write or talk, you can kind of think about what you're going to say next, but you can only say one thing at once, and so you have to express yourself in a sequence, like in a like just a sequence that goes along. It feels a little bit more like that, like, the model can have this internal representation of what it's planning to do next. Like, we don't know. Probably there's something in there of like that kind of type of phenomenon. But it's just going one at a time, in the same way that I'm talking one at a time. I can't say my entire thought like splat all at once. Same thing when I write. Like, I might write a document in a hierarchical way where I first write a plan, then I flesh out each bit, but I'm still writing each individual like token one by one. And that's just like, I don't know, something to do with time, I guess. Like maybe a human doesn't exist outside of time and can't just like continually like simultaneously write an entire document in like one big go. You can only do one thing at a time. And like, why we think that a model that can only do one thing at once and does go in like, a single direction can't be like a, generally intelligent system. Like, I don't see why that's important. You might say like, hey, it's easier if the model can observe everything at once and kind of contextualize across. That's just a engineering detail in a way.
Yeah, but in a way it's kind of anthropomorphic, because I was reading The Language Game by Nick Chater and Morten Christensen. I've interviewed them as well, and they called it the now or never bottleneck, which is that, human attention, it's almost like a razor point. We can only pay attention to one word at a time. Even in our visual field, most of it's discarded. We only just, take in a very small amount. So the remarkable thing is that that's the way that we've learned to communicate with language. And presumably it's, I guess, a good thing to mimic that in a language model.
It might be a good thing, or it might just be sufficient.
Yeah.
And it may not be optimal, but like for models that, like, I'm going to keep it constrained to text and language, they're training to model text and language, and all of that, except for the last year or two, has been written or generated by humans. And so because they think word by word, you can model these things like that way pretty successfully. Maybe a counter argument is like, the way I generate a document, if say I'm writing something, like I'll write my plan and then I'll go through and I'll edit it. But the final finished piece, that's the thing you observe and the model tries to generate.
Yeah.
That's why, it's pretty straightforward and intuitive why things like chain of thought and stuff like that works. It's because you're basically, it's sort of part of the necessary process for actually like producing a good finished product, when you can only go left to right. Like very few people like write a perfect document or some like finished polished piece of work by just like writing their paper like start to finish. Effectively all of that like intermediate like writing and rewriting is human chain of thought that doesn't always get observed, but if you get a model to do it, suddenly you get these big improvements. This like internal monologue almost is useful.
Patrick, it's been an absolute honor to have you on MLST. Thank you so much for joining us today.
Thank you so much for having me. It's been great. Love it.
Cool. Great.
Thank you.